In previous videos, we've seen a one-period bargaining game, the ultimatum game. We've seen a two-period bargaining game, where both players get a chance to make an offer. And now let's look at what happens when there's no predetermined end to the bargaining game. So the offers keep being made, so offer and counteroffer, until eventually something gets accepted. The only way the game can end is when somebody accepts an offer. So this is going to be just like the two-period bargaining game that we've analyzed in an earlier video, except that the game doesn't end until someone accepts an offer. So player 1 makes an offer in the initial period, player 2 makes an offer in the second period, player 1 makes an offer again in the third period, player 2 goes again in the fourth period, and so forth, until somebody accepts an offer and the game ends. In other words, in odd periods, player 1 makes an offer, and in even periods, player 2 makes an offer. So in period 1, player 1 makes an offer, and the game ends if player 2 accepts that offer. In period 2, player 2 makes the offer, and the game ends if player 1 accepts. Things get different from what we've seen before because now there's a period 3. Now player 1 again makes an offer, and again the game ends if player 2 accepts. And this keeps going on. So in general, in period t, where t is odd, player 1 makes an offer, and the game ends if player 2 accepts. And in the next period, so if t is an odd number, t plus 1 is an even number. So in the even round, player 2 makes an offer, if the game gets to that round. And this carries on until somebody accepts. Now, how would we draw a game tree for this? It's a little more challenging because there's no end to this game. Yes, the game ends when somebody accepts, but if they keep rejecting, the game never ends. So how would we draw a game tree? It's not really possible to. If we start drawing the game tree, the beginning would look something like this. The initial parts look just like the bargaining game we've seen earlier. So in period 1, player 1 offers M1 between 0 and 1, and player 2 can either accept or reject. If he accepts, then the payoffs are determined by M1. I'm going to use a subscript here to denote the period in which that offer was made. So if in period 1, player 1 is going to offer M1 1, and that, if it's accepted, will lead to a payoff of 1 minus M1 1 to player 1, because he keeps the rest, and player 2 gets whatever is offered, M1 1. However, if it's rejected, the game proceeds to period 2, in which case player 2 makes the offer. So we denote the period in which the offer is made with the subscript, and I'm going to denote the player making the offer with the superscript. So player 2 makes the offer, and he chooses an offer between 0 and 1, and then player 1 gets to accept or reject. If she accepts it, then she receives the amount that player 2 offers her, which is M22, but that payoff is discounted by her discount factor. Player 2 gets to keep the rest, but again that's discounted by his discount factor. If she rejects it, then we continue to period 3. And in period 3, it's an odd period, so player 1 again makes the offer. So player 1 makes the offer in period 3, and she picks M13. And again, that's a number between 0 and 1, and player 2 can accept or reject. If he accepts, the payoffs are given by M13. He gets M13, she gets 1 minus M13. The payoffs are discounted accordingly. Because they're 2 periods out, the payoffs are discounted by the square of the discount factor. However, if player 2 rejects, then we proceed to period 4, and so forth. But we can't use backwards induction. We can't start at the very last period and work our way backwards. Not only can we not use backwards induction, but when you try to figure out what a strategy is for each player, you're going to realize that this is actually a very complicated object. So let's look at what a strategy would be for player I. What are the decision nodes for player I? There are many, many decision nodes for player I. So we want to understand what is a strategy for player I, where I could be 1 or 2. Remember that a strategy has to tell you what the player is going to do at every single decision node. So for each player, their strategy has to tell us, given the sequence of offers that have been made in the past, when it's your turn to accept or reject, do you want to accept or reject the offer that was just made? And given the sequence of offers that have been made, what is the offer that you would like to make next? And this has to be for every possible sequence. So take just any sequence of possible offers, M11, M22, M13, M24, and so forth, where for every t, if t is odd, M1t is the offer that player 1 could have made in period t, and M2t is an offer that player 2 could have made in period t for t even. So take any such sequence, M1 through M2t for some even t, then for player 1, there's a decision node, first to accept or reject this last offer made in the even period by player 2, and then to pick in the next decision node an offer to make in period t plus 1. That means that there's a very large number of decision nodes where player 1 needs to make a decision of accept or reject, and a decision of what to offer next. Similarly, for player 2, after every possible sequence of offers M11 through M1T for any odd T, there's a decision node for player 2 to accept or reject the offer M1T that player 1 made in the period T, which is an odd number T, and then to pick an offer to make in the next period T plus 1. So these strategies are these very, very high-dimensional, complicated objects. There are many, many, many decision nodes, and the strategies need to tell us what the player is going to do at every single possible one. So a strategy has to tell you whether to accept or reject the last offer made, when it's your turn to accept or reject, and then when it's your turn to make an offer, it has to tell you what to offer. And this can, of course, depend on all the offers that had been previously made. What we're going to do, however, is to cleverly use the recursive structure of the game. What do I mean by that? Let's go back and look at the game tree that we have and notice something important about it. Look at this subgame. The subgame starting at period 3. What's remarkable about this is that this subgame is identical to the original game. So after the first two periods, it's as if they start the game over again. The only difference is that they're going to discount the payoffs. But aside from the discounting, the game is identical to the original game. And we can use that to simplify the analysis. So we're going to leverage that recursive structure of the game to simplify things. So let's suppose there were an optimal M1 in some equilibrium to offer here. If it's optimal in an equilibrium for player 1 to offer M1 here, why would player 1 do anything different here? We would think that player 1 would behave exactly the same here, because the decision that player 1's making at this node is exactly the same as what they're making here. The game they're looking at is exactly the same. So when they look down this game tree, they see the same thing from here that they see from here. Similarly, for player 2, the game from here looks exactly like this game from here. So we should quite reasonably expect that player 1 is going to offer the same thing here, and player 2 is going to offer the same thing here and here. If we can find an equilibrium like that, that's what's called a stationary equilibrium. It says that when you play a subgame that looks exactly the same as the original game, you're going to behave exactly the same in both situations. So we're going to try and solve for a stationary subgame perfect equilibrium. Now let's suppose we had a subgame perfect equilibrium where player 1 offers M1 and player 2 offers M2 in the first and second periods respectively. Let's suppose that this equilibrium is such that the offer made in the first period is accepted immediately. And in general, in each period when somebody makes an offer, it's accepted immediately, because there's no reason to make an offer that's rejected, as we've seen in our earlier analysis. So in this stationary equilibrium, if player 1 is going to offer M1 and player 2 is going to offer M2, and these offers are going to be such that the offers are going to be accepted immediately and not rejected, then the payoff when M1 is proposed and accepted is 1 minus M1 and M1 respectively. So should we get to the third period, that's going to be the division of the surplus. So the continuation payoff from entering the third period would be these, but discounted. So if we end up in the third period, these are the payoffs that they're going to get. From the perspective of period 3, if we're already in period 3, it's as if player 1 gets 1 minus M1 and player 2 gets M1. But from the perspective of the start of the game, they discounted by 2 periods. So it's delta 1 squared times 1 minus M1 and delta 2 squared times M1. So if we prune the tree and draw the pruned tree, it would look like this. We replace the subgame that starts in period 3 after player 1 rejects player 2's offer, and we replace that with the payoff that they would get should the game proceed to period 3, so the continuation value. Once we've done that, we've got this simplified game, and now we can solve for what M1 and M2 ought to be. Remember, if player 2 is going to make an offer that player 1 accepts in an equilibrium, it has to be that player 1 is indifferent between accepting and rejecting. So player 1 has to be indifferent between these two. So these two numbers have to be the same. The payoff from rejecting and accepting to player 1 has to be the same. So indifference for player 1 says that delta 1 M2 has to equal delta 1 squared times 1 minus M1, which means that if we solve for M2 in terms of M1, we get M2 has to equal delta 1 times 1 minus M1. If player 1 is going to make an offer that player 2 is going to accept, then player 1 is going to offer, as we've seen earlier, to player 2 just enough so that player 2 is indifferent between rejecting and accepting. If player 2 rejects, then player 2 is going to get this. Remember that we calculated here M2 such that M2 is so that player 1 would accept. So should the game go to player 2 making an offer, this is the payoff that player 2 would get. So it has to be that player 2 is indifferent between accepting and getting this payoff and rejecting to get this payoff. So indifference for player 2 says that M1 has to equal delta 2 times 1 minus M2. Now we've got these two equations, and so we can solve for M1 and M2. Substituting 1 into 2, we have M1 equal delta 2 times 1 minus delta 1 plus delta 1 times M. So that's equal to delta 2 minus delta 1 delta 2 plus delta 1 delta 2 times M1. So M1 times 1 minus delta 1 delta 2 is delta 2 times 1 minus delta 1. And therefore, M1 is delta 2 times 1 minus delta 1 divided by 1 minus delta 1 delta 2. And plugging this back into equation 1, M2 is delta 1 times 1 minus delta 2 divided by 1 minus delta 1 delta 2. We've shown that this is a stationary subgame perfect equilibrium for player 1 to always offer delta 2 times 1 minus delta 1 divided by delta 1 delta 2, and for player 2 to always offer delta 1 times 1 minus delta 2 divided by 1 minus delta 1 delta 2, and for each of them to accept the offer as long as the offer is at least as high as this. Moreover, this is actually the unique equilibrium. The resulting payoffs are 1 minus M1 for player 1 and M1 for player 2. So if we plug in what M1 is, we find that player 1 gets 1 minus delta 2 divided by 1 minus delta 1 delta 2, and player 2 gets delta 2 times 1 minus delta 1 divided by 1 minus delta 1 delta 2. So we see then that the bargaining power is a function of both players' patience, or their discount factors. The more patient my opponent is and the less patient I am, the lower my bargaining power. So my bargaining power is decreasing as my opponent becomes more patient. So let's think about this from player 1's perspective. Let's fix delta 1 and take delta 2 to get closer and closer to 1. Then this numerator gets closer and closer to 0. On the other hand, from player 2's perspective, if we fix player 1's patience and increase delta 2, as this gets closer and closer to 1, this thing stays constant, but this thing approaches 1 minus delta 1, so pi 2 approaches 1 as delta 2 approaches 1, fixing delta 1. So the more patient I become, fixing my opponent's level of patience, the higher my bargaining power. The idea here is that if I'm willing to say, I don't care, let's let the bargaining process continue, then I have a higher bargaining power. On the other hand, if I'm very eager to finish the bargaining, then I have less bargaining power. Another interesting subcase is where delta 1 and delta 2 are equal. So when delta 1 equals delta 2 equals some delta, and you then say we take the limit as delta goes to 1, then the bargaining power of both players reaches a half. If delta 1 and delta 2 are both the same in their delta, then pi 1 is 1 minus delta divided by 1 minus delta squared, so it's just 1 over 1 plus delta. And pi 2 is delta over 1 plus delta. And so as delta goes to 1, these both converge to a half. How do we interpret that? Two equally patient bargainers are negotiating over a very long horizon, then they have equal bargaining power. That's what we can interpret from this.